right. Our next speaker is Nick Ezzell, who has been studying in the physics department at the University of Southern California. Did his practicum at Los Alamos.
All right. All right, hello everyone. Okay, thanks. So I'm going to be speaking about a variational approach to quantum tomography. And I first want to immediately thank the fellowship for allowing me to do this work, because this was my practicum work at Los Alamos National Lab, which includes, of course, people who worked at LANL. It would be weird if not, but unsurprisingly, also many collaborators who were also visiting LANL at the time. So I would also like to thank them for the talks and for the various projects that we worked on, which I didn't think about it at the time this way, but when trying to construct a talk, retroactively, they kind of fit under two categories, which you could call quantum tomography, and specifically state and process tomography. And if you want to make this kind of diagram, you might say, well, these are theory papers and these are experiment papers. But roughly speaking, we did quantum tomography. And I don't expect the majority of people to be an expert on quantum tomography or the word variational. So my first task will be to try to define these things in an informal way, and then slowly add more formality as we go until we get to where I think is the limit of formality. So first of all, let's begin with some etymology. So when I see a new word, I like to know the etymology, but usually I don't, so I have to look it up. So it turns out for tomography, tomos and grapho make up the word, which mean a slice or section, and to write or describe, which pretty accurately describes what tomography means scientifically, which is to describe an object by a series of cross-sections. And if you like examples, then here's an example of tomography in which I'm presenting to you one slice of an object, and basically in my front area in my apartment. And if you just looked at this slice, then you might conclude that this is some sort of bush or tree. But if I show you the other images, then you would say that this is a CAT scan. So I don't know if you can see, it's kind of dark, but this is my cat Mitsu in the tree. And continuing on, because this is a quantum talk, my next example will be to talk about variational approach using my other cat, Junie. So the goal will be, before we kind of defined an object by decomposing it into a series of cross-sections. But now I'd like to say that in many cases, it's more useful to think about how to define an object constructively. So rather than what do you decompose it as, how do you build it up from scratch? And so I'm going to say I want to build up an image of my cat from scratch, but this is just some toy example. So I'm just going to give you a movie about how that might look like, and just to tell you what the key ingredients of a variational algorithm are. So the first ingredient is you need an ansatz. And I started with, to restart the movie, a gray image, essentially. And you need a cost function, an update rule, and a stopping criterion. But because this is some toy example, I didn't spend a lot of time thinking seriously about good ways to define these things. I really just interpolated, so it's kind of a cheating little image. But that would be how a variational algorithm would look like. You have some guess, and it interpolates to the end, usually by more clever methods than strict interpolation, which says that I already had the answer. And next, I would like to discuss a slightly more formal introduction than two pictures of my cats. And I don't expect everyone to be familiar with quantum theory, although we heard a talk this morning about similar things. So if you heard that talk, this should be a reminder. But if not, no worries. I'll go over it again. So I'm going to start with a single qubit. And you may already know that, but if you don't, it can be represented by a 2x2 matrix. And I've decided to parameterize it by three real parameters, Vx, Vy, and Vz, which satisfy this norm inequality. And due to this norm inequality, we can picture it on some sort of block sphere, although more accurately, we should call it a block ball, because the norm could be less than 1. And the essential essence of tomography is to estimate what these values of Vx, Vy, and Vz are using valid rules of quantum mechanics. So you prepare a state, an input state that we want to learn, say, and you're allowed to make measurements. For example, you can measure the Vz component of this vector. And if you want to measure the other components, you first rotate the sphere and then measure the Vz component. And just for the sake of making it seem the probabilistic nature of quantum mechanics to sort of make sense, I've kind of said that it's kind of like asking, is VZ positive? In the sense that if VZ, it's actually a continuous variable from -1 to 1, but if it were 0, the measurement outcomes would look like getting 50% -1 and 50% 1. This isn't exactly precise, but that's okay. You usually don't have to be. So, but most of the time we're interested in more than one of an object. So what happens if you have n qubits? Well, in that case, now we have a matrix which has an exponentially large dimension in n. It's 2 to the n by 2 to the n. But in this prescription of thinking about this vector v, which we call the coherence vector, you can just say that this coherence vector has d squared minus 1 values. And the goal of tomography is to reconstruct these d squared minus 1 vj values, essentially by just estimating each of them individually, which thereby requires an exponential number of measurements and also requires you to store those exponential number of floats in the end. But even if you manage to do this exponentially long process that requires so much memory, well, now you're stuck with an exponentially large matrix that you have to manipulate. So any downstream application is also exponential in time and memory. So that comes to this idea of a variational approach, which is that we want to think about how you might define a quantum state constructively and whether that gives you any advantages to the time or memory complexity of storing and manipulating the state. And in our case, quantum computing is a pretty big field now, so the tools of the trade are somewhat well established to quantum practitioners. And one way to think about what a quantum state is that it's the process of starting in some known state and applying a valid quantum circuit, which consists of various logic gates. But ultimately, if you're not familiar with quantum, you can just say that this is a particular type of matrix decomposition. It's not really like a QR or anything like that, but you can think of it that way, and that's fine. And what I'm saying is that I'm going to decompose a guess for generating a quantum state in this particular type of matrix decomposition, which has variational or learnable parameters, theta 1 through theta 6 in this example. And the nice thing about this construction is that, well, if we're able to find angles of which prepare the state we're interested in, then by design, storing the information about the gates we're applying and the angles is efficient to store. I can intentionally make it where we're only storing a small number of parameters. And it's also efficient to prepare quantumly. So any downstream application that I want to do, like measure an observable, well, I have an exact way to prepare this on a quantum computer, and I'm not forced to contend with this exponentially large matrix. So to put this into perspective, I just wanted to give an example. So let's just say we have a 2-qubit system, which roughly looks like 2 block spheres, but not really. So I kind of put this connection to indicate that there's something else going on, but don't worry about it. So I'm thinking about this as being a realistic quantum state, which is coupled to a bath. So it's in thermal equilibrium. So the statistical mechanics people in the room might say, well, it's some Gibbs state. If you're unfamiliar with this kind of formulation, don't worry, because you can also just think about this as a matrix where I've specified what's called the inverse temperature and some Hamiltonian H. But you might notice that when I specify those two things, that this matrix has several zeros. And essentially, sort of hand-waving a bit, the idea is that these zeros appear because there are symmetries in the system. And so we don't need all of the entries of the matrix to specify the quantum state. And so if we can try to come up with an ansatz which is aware of those symmetries. And also, if you actually computed the rank of this matrix, it's approximately only rank 2, despite being 4 by 4. And that's because I've chosen the inverse temperature to have a small temperature. And if that makes sense to you, great. Otherwise, it's just actually no full rank matrix. And so the ansatz I came up with respects those two ideas. And essentially, long story short, you just compare. It has zeros in the same places. So it's doing a good job of at least saying, OK, where should these non-zero values be? And because I actually don't know in principle what exactly the Hamiltonian is or the inverse temperature, I have to specify random angles to begin with. And when I do that, I have to then train these angles in order to prepare the state I actually want to prepare. And so here I'm just showing some movie where I did that. And you see that the final matrix I end up with if you just stare at it for a second and compare it to before, it's the same exact matrix. So we can successfully prepare these states in this variational way, which you might can call variational compiling. I know I haven't defined all of the ins and outs of the algorithm because that would require me to get into some of the weeds. So I just want to comment on a few of the results for a moment. And then at the end, I'll try to talk a little bit about the weeds and conclude there. So first of all, if you're curious, the states I'm manipulating or trying to find a circuit to prepare are these XY Hamiltonian states. But if you don't know what this is, they're just some matrix. And in the top plot, I'm essentially just plotting. This is a measure of how well I was able to compile the state. So when this thing is 0, I've done a great job. And the thing I just want you to take away from this is that all the values are very small. So in the worst case, it's on the order of 10 to the minus 7. And what I've done is I've plotted this scheme as a function of the number of qubits. And what I wanted to do was compare the number of iterations it took for me to compile the state compared to naive tomography, which has an exponential scaling. And you see that the scaling is much more favorable empirically. And that's because I exploited the structure in the system, and I, by design, used an ansatz which doesn't have an exponential amount of overhead. And one thing I wanted to mention is that whenever I do any project that involves any amount of coding, one thing I learned at the first supercomputing conference is, well, you should share literally everything you did, because otherwise, especially for the quantum world, if you did any quantum experiments on a computer, which I'll show next, it's important for reproducing it that you share. So here, I've shared this code. And it's one practice that I took away from the fellowship, that anytime I ever have code, I will share it with the paper and cite it with the paper. And generating these, or verifying our algorithm works classically, required HPC resources, both at LANL and USC, when I continued the project. Because, for example, the optimization of a single point on this box plot took on the order of 10 hours or so, and I generated hundreds of them. So it took several thousand hours of compute time to get this kind of single box over here. And this is just for one class of states, and we did several different classes. And so we also ran this experiment on actual quantum device, which anyone in this room can sign up and use right now. So IBM, if you just want to run sort of small-scale experiments, you can do so. And I don't want to get into all the details of this figure because I think it will quickly get lost, and I'll have to talk about the quantum computer. But one thing I wanted to point out is that in the end, if you look at the spectrum of the original state I was trying to learn in this blue, and you look at the spectrum of the thing I learned when I learned the cost to an order of 10 to the minus 2, you see that essentially what I did is I kind of only learned the first principal component. So to get a rough approximation, it was good enough to learn the first eigenvector, the eigenvector associated to the largest eigenvalue of this matrix. And in fact, that's a good way to think about this procedure, that part of the value of this ansatz approach, this variational approach, is that you can control the rank of your approximation. But that forced us to ask the question, well, what is the optimal state that is a low-rank approximation? And so I'll say it precisely in a second here, but many of you are probably familiar with the classical low-rank approximation problem, and some people have even discussed it in some of the previous talks. And what we found is that essentially we have the same structure to our problem. We have a known matrix, and or at least in theory, rho, and we have a sigma which we want to find, which is rank constrained, that is closest to rho. But in the quantum space, we're interested when these things are normalized, so that has a trace 1. And also this p is what's called a Shatton p norm. But for p equal 2, it's the Frobenius norm that probably many of you have heard of. And the interesting thing is that we found the solution is the classical one. So this first part is you project onto the principal component subspace, plus an additive normalization. So normally when people say, you just normalize, I would divide this thing by the trace of this truncated subspace. But actually, you make an additive normalization. And intuitively, it's additive and not multiplicative because this one has a higher entropy. But if you don't like intuition, then read our paper and you'll look at the proof. But one of the nice things we're also able to show is that in the case of the one norm distance, the solution is not unique. And for the two norm distance, it is unique. And all I'll say about that is that's important if you care about the interpretation as principal components. And was interesting to us because if you ask a quantum information theorist whether you like trace distance or Hilbert-Schmidt, they will laugh at you if you talk about Hilbert-Schmidt, and we can discuss that if you like to hear about those kind of things in the quantum information field. And it looks like I want to leave time for questions, so I won't actually talk about this, but we also proved various things. We chose a cost function that was Hilbert-Schmidt for that reason, among others. And here they are if you're just kind of curious. And finally, I didn't really have time to talk about the other paper, so I just wanted to show one main result from it, if you want to hear about process tomography, which is that you can find a variational circuit to learn an unknown unitary U using only poly K product states, which was a very non-trivial theoretical result that we derived. But I'm not going to try to explain it in the remaining 4 minutes and 30 seconds I have for questions. So please ask questions